Module 5, Fluctuating Stress. Now we have seen that in fatigue, the component subjected to fluctuating loads, which in turn causes fluctuating stress. So how do we characterize the fluctuating stress? The forces and in turn the stresses are in general fluctuating in nature. The fluctuating stress phenomena can be shown by the figure below. This figure shows the fluctuating stress phenomena occurring in a body. This is the stress pattern which varies with respect to time. So this fluctuating stress can be characterized by several parameters which are shown here. So what are the parameters which we use for characterizing the fluctuating stress? The main parameters are, we have the sigma max, that is a maximum stress, sigma min, that is a minimum stress, then we have sigma em, that is the mean component of stress, mean component of fluctuating stress. Then we have sigma a, which is the alternating component or the amplitude component or the reversed component. Of the fluctuating stress. Then we have sigma r is the range of stress. Then we have sigma s, which is the steady or static stress. So what is this parameters? Sigma max, these parameters are shown in the figure. Sigma max is the maximum stress coming in the phenomena. This is the maximum stress coming in this kind of a loading. So this is sigma max. Stress corresponding to this point is called the sigma max. Minimum stress is the stress corresponding to a minimum point in the stress time curve. That is this point. The stress corresponding to this point is called the minimum stress. Then this fluctuating stress can be represented by two components, mainly the sigma mean, which is a mean component of stress, and the amplitude component, which is sigma a. So if we draw this curve, this can be represented, the total sigma can be represented as a combination of sigma m and sigma a. And then we have a range of stress and the steady stress or static stress. So the steady or static stress is nothing but the stress which already exists in the body. Is nothing but the stress which already exists in the body or exists in the component. This is something like the preload in the component. Example will be preload in components, or the spring stiffness. If we use springs in this springs in the assembly, then initially it is compressed and kept in place, so it has a compressive preload in the component. That is called the static or steady stress. Then sigma mean, we have already seen. Sigma m is, I told that sigma m is the mean stress. This can be written as sigma max plus sigma min by 2. And the alternating component or amplitude component sigma a can be written as sigma max minus sigma min by 2. So any fluctuating stress phenomena can be expressed as a combination of sigma mean and sigma a, sigma alternating. And this another few parameters called stress ratio, that is R, is nothing but sigma min by sigma max, and the amplitude ratio is nothing but sigma A by sigma M. So if any of this parameter is given, then we can find out the remaining parameters. Like if sigma min and sigma max is given, then we can find sigma M, sigma A, stress ratio and amplitude ratio using this formula. Or if the stress ratio and the amplitude ratio is given, then we can find out what will be the sigma max and sigma min and sigma A and sigma M, so individually. So this is how we characterize a fluctuating stress. Thus we have seen sigma M, the main component of stress is sigma max plus sigma min by 2, or the alternating component or the amplitude component of the fluctuating stress is given as sigma max minus sigma min by 2. The stress ratio is given as sigma ratio of sigma min to sigma max. Amplitude ratio is the ratio of sigma A to sigma M. So these are the different parameters which are used for characterizing the fluctuating stress. Therefore, for a completely reversed loading, for completely reversed stress, we can say R will be minus 1. That is sigma min is equal to sigma max, and one is in tension, one is in compression, so it will be something like this. So this is the case where sigma mean is equal to 0. Therefore, for completely reversed stress, we can say sigma m is equal to 0. And sigma A will be sigma max minus sigma min by 2. That's equal to sigma. If sigma max will be, say sigma min will be minus sigma. That is, the minimum value of stress is minus sigma and maximum value of stress is plus sigma. Both are same value. So this becomes, if we say sigma minus sigma by 2, that's equal to sigma. If alternating component is sigma and the mean component is equal to 0 for the completely reversed stress. And for repeated stress, so this I can say is 1, this is 2. For repeated stress, R equals 0 or sigma min equals 0. That can be represented as so here sigma min is equal to 0. So this is fully tensile in nature. Therefore, repeated stress is fully tensile in nature, whereas completely reversed stresses has a tensile as well as compressive cycles. And here will be sigma max plus sigma min by 2. In this case, we can say sigma max is equal to sigma min is equal to 0. So this will become sigma by 2, will be sigma m. Sigma A also will be equal to sigma by 2. Therefore, for repeated stress, the main component of stress is equal to sigma by 2 and the amplitude component is sigma by 2. And for the completely reversed stress, main component is 0 and amplitude component is sigma. So these are the different parameters which are used to characterize the fluctuating stress in general. Now, till now we have considered an ideal case. We have not considered the presence of a notch. So what happens if the notch is present? What happens in presence of notch? We know that stress concentration factor need to be considered in presence of a notch. So two cases are there. In the absence of notch, sigma m and sigma A will take nominal values. Say sigma M 0 and sigma A 0. In presence of notch, sigma M and sigma A are modified by the stress concentration factor, the fatigue stress concentration factor. So how it gets modified? In case of a ductile material, we have seen that when the stress levels are very high, as in case of a notch where we have a concentration of stress near the notch, local yielding takes place. Local notch yielding takes place, which results in strain hardening of the material. So while dealing with the static loads, we have seen that for ductile materials, stress concentration factor need not be considered, because even if the stress concentration of stresses takes place, the material yields locally and strain hardens. So thus this does not affect the functional properties of the material. But in case of brittle materials, we saw that there is no strain hardening or no yielding taking place. Therefore, stress concentration factor has to be taken care for the brittle materials. Now for ductile materials, in presence of a notch, the fatigue stress concentration factor has to be applied. Concentration factor has to be applied, and now sigma A becomes Kf into sigma A naught, and sigma M becomes Kf into sigma M0, where sigma A0 is the nominal stress amplitude or amplitude component of stress, and sigma M0 is the nominal mean stress. So this is when the stresses are much below the yielding. Even if we have a stress concentration, if the stress values are less than the yield, then stress concentration factor has to be applied for amplitude component as well as mean component. But it has been found out that in presence of notch, the localized notch yielding occurs, and which is accompanied by strain hardening, which we have already seen. Therefore, the nominal mean stress method, there is a method called nominal mean stress method. This suggests that when the stresses cause the local yielding of the member, sigma M need not be multiplied by the stress concentration factor. That is, the mean component of stress does not get modified by the stress concentration factor, but the amplitude component will get modified. This is important. This is by nominal stress method says that when the stresses causes the local notch yielding, then mean stress is nothing but the nominal mean stress only, but the amplitude stress gets modified by the fatigue stress concentration factor. Here Kf is the fatigue stress concentration factor. In the previous module, we have seen what is a fatigue stress concentration factor and how much it is different from the theoretical stress concentration factor. We have seen that fatigue stress concentration factor depends on is related to the static or theoretical stress concentration factor by a parameter called the notch sensitivity of the material. So therefore we can summarize as follows. If local notch yielding occurs, then sigma m equals sigma mo, and sigma a is equal to k into f, kf into sigma a naught. This is first case. In the second case, if local notch yielding does not occur, then sigma m equals kf into sigma m naught, and sigma a is equal to kf into sigma a naught. So this is a phenomena which happens in brittle materials. In brittle materials we don't have any yielding occurring. So in brittle materials, sigma m is taken as kf into sigma m naught, and sigma a is kf into sigma a naught, where kf is the fatigue stress concentration factor. Now, so in this module we have seen how to characterize the fluctuating stress acting in a component. That is, any fluctuating stress can be expressed in terms of the various parameters like the mean component of stress, amplitude component of stress, then we have the stress ratio, we have the amplitude ratio, we have the range of stress. So with these parameters we can characterize any kind of fluctuating stress acting in a material. Now in the next module we will see, with this kind of a fluctuating stress acting on a body, how to design the member against failure. So that is the fatigue failure criteria which we will be deriving in the next module.